Transmission, reflection, and interference. In this lesson, we're talking about wave behavior, sound behavior in different mediums, the transmission of sound, sound in space, sound reflection, echolocation, and then interference of waves. Wave behavior. If the medium the wave travels through stays constant, the waves will travel at a uniform speed. Waves act differently as they pass through different mediums and encounter various conditions. And if the wave encounters an end, fixed or free, wave reflection will be observed as shown below. So if it's a free end, as in the end of the path of the wave isn't attached to anything, so think of a string attached to a wall. So in this case, a free end, there's no wall that it's attached to. So it's just able to go along the ground. So if we start up, it comes back up. So you can see in diagram 1, we're starting up and we end up. If it's a fixed end, however, and we have a wave that starts up, we're going to finish down after it reflects off the fixed surface. Sound behavior in different mediums. Sound waves are transmitted from particle to particle through vibrations. The closer the particles are, the easier it is to vibrate into their neighbor. Therefore, sound travels faster in solids than liquids, liquids to gases, and denser mediums. So again, the particles need to vibrate back and forth. If they are closer together, it's easier for them to do that. If the particles are closer together, when they vibrate slightly, they'll still make contact with the one beside them. If they're in a gas and they vibrate slightly, they're not going to contact the molecule nearest to them, so that sound energy won't necessarily be transferred from one molecule to the other. However, in a solid substance, if you vibrate even a little bit, that molecule is going to transmit the sound to the neighbor. And then as it says, denser mediums, so things like steel is more dense than air, and therefore it's going to transmit sound faster than in air. Now you can test this out for yourself. Tap your desk with your knuckles and listen to the sound it makes. Now make sure you do this tap lightly, because for the second one, you're going to want to do it again lightly, but you want to do it the exact same amount. So next, put your ear to the desk and tap the desk again. Again, try not to make it too hard, because the sound will be pretty loud. And then compare the two sounds that are made. Which one's louder, and why do you think that is? Refer to the previous slide for the answer to that question. However, since liquids have less energy and less motion as a result than gases, it takes a greater amount of energy to begin the vibration. So for this reason, a faint sound in air wouldn't be transmitted in water because it wouldn't have enough energy to vibrate the atoms. So gaseous substances, they're already going to be moving at a lot faster pace. So they're going to have a lot more velocity just to begin with. So if you give them a little bit of energy, there's a better chance that they're going to run into each other than if you give liquids a little bit of energy, because they might not make contact with each other because they're not moving as much. They don't already have as much energy to begin with. So when you give them that little push, they still might not run into each other. However, we said on the previous slide, since they're closer together, the chances of them running into each other are still greater, but with a lesser amount of energy, they may not have enough energy to get going to meet that neighboring molecule. In space, there are so few particles, and they're really far apart, the ones that are there. And since the particles can't vibrate against each other, sound waves can't be transmitted across empty space. Sound behavior under different weather conditions. Sound waves travel faster in higher temperatures due to the increased energy of the particles, like we were talking about before with the gas compared to liquid and solid. Gas particles already have a higher amount of energy, so we can transmit that sound easier. Hot particles are going to be moving faster than cold particles, so it's going to be easier to transmit that sound in hot particles than in cold particles, because they're already moving a little bit more. They already have a little bit more energy, and therefore it's easier to transmit the sound from one particle to another. And we can see that here. If we compare apples to apples, so air to air at a higher temperature transmits sound faster than air at a lower temperature. And same thing with water. Partial reflection off a boundary. When a wave is transmitted across a boundary of two different mediums, i.e. a wall, some of the energy goes into the second medium, but some is also reflected back. This means that if you're trying to talk through a wall, a lot of the sound energy will be absorbed by the wall, and the person on the other side might not hear you. So in this picture here, we can see a lot of sound energy being directed towards the wall. Alright, we're transmitting the sound that way. Some of that sound energy is going to bounce off the wall and come back towards the person, and only a little bit is going to make it through. Now, if this amount that makes it through is not enough to be heard on the other side of the wall, then you're not going to hear that person. Because not only is some of the sound being reflected off, like we showed here, but some of it is also being absorbed by the wall. So the molecules in the wall start to move a little bit back and forth, and that's taking away some of the energy. If there's not enough energy to actually make it through the wall completely, to vibrate the particles of the wall all the way through, then you're not going to hear anything at all on the other side. Wave reflection off a boundary. For the reflection of any wave, whether it be sound or light, the angle of incidence equals the angle of reflection. So this angle here, angle of incidence, is going to equal this angle here, the angle of reflection. Wave reflection off a boundary. This reflection is very apparent regarding how sound is perceived and used. Some animals, as well as submarines, use echolocation to locate objects. Now, when we're talking about submarines, we're actually going to talk about something called sonar, which is a similar thing. This is an artificial production of these waves compared to what animals use for echolocation. Sound waves are bounced off various objects such as prey, land formations, etc. for the bat or the submarine or the dolphin so that they can see what's in front of them. By analyzing the reflected wave, the size, location, and shape of the object can be determined. So you can see in a picture on the right-hand side here, the bat is going to emit these blue waves. The blue waves are going to hit this object right here. It's going to be its dinner, hopefully. It's going to bounce off the dinner, come back towards the bat, And then from the reflected sound waves, the bat can determine how far away the dinner is and how large it is. Interference of waves. Interference is what occurs when two waves meet. There's going to be two kinds of interference, destructive interference and constructive interference. In destructive interference, we get a crest meeting a trough. So in this case here, we get a crest here, and we have a trough here. Now, if they both have the exact same amplitude and shape, we're going to get complete interference, and we're going to get nothing as a result, and that's going to occur at the node. That's where they're going to come together, and you can see we're just flatlining. Once the waves pass, they resume their original amplitude. So you can see this guy here that was the trough and is now the trough again is exactly the same as it was before, and what was the crest and what is now the crest again is exactly the same as it was before after the interference occurred. Constructive interference. Constructive interference occurs when a crest meets a crest or a trough meets a trough. The amplitudes are added, creating a supercrest or a supertrough. So you can see in the top example, we can consider this a 1x or a plus 1 and another plus 1 coming together. And what happens is that they create a plus 2 or a 2x. It's going to be twice the height, exactly the same shape, because our crests are added together. 1 plus 1 equals 2. So we get a crest that's twice the height of the original ones that came together. And then once they pass, they go their separate ways with their original size and shape. Interference. If only two waves meet, they regain their original amplitude and shape once they pass, like we just showed in the previous example here. That's what we're talking about right now. However, if the waves are continuous, as in we're making the disturbance over and over and over again, like we see in these pictures here, the interference will continue. So if you get constructive interference where the waves are in sync to each other, you can see this guy and this guy are both lined up evenly, then you're going to get the additive, and it's going to keep adding over and over and over again, and we're going to end up with this guy on the right. However, if it's destructive interference, as in they're out of phase, so you get a trough meeting a crest, then what happens is you get continual nodes. So these guys are going to cancel each other out and make a node there. These guys are going to cancel each other out there and make a node there, and so on and so on. So you're going to get a flat line all the way across. Check your understanding. Being as accurate as you can, draw what occurs when a crest of plus 1 meets a crest of plus 1. B, a trough of minus 2 meets a crest of plus 3. And C, a crest of plus 2 meets a crest of plus 1. So I want you to pause the video and try these three questions. Okay, let's see what the answers look like. So we get a crest of plus 1, so let's do this. And it's going to meet a crest of plus 1. So that guy's going that way, and we're going to meet a crest of plus 1 going that way. So as a result, they're going to add together, and we're going to get a crest of plus 2. So that's plus 1, and what we get is a crest of plus 2. Now how about a trough of minus 2? So minus 2 meets a crest of plus 3. Now what results is going to be a crest of plus 1, because the plus 3 plus minus 2 equals plus 1. And then see, a crest of plus 2 meets a crest of plus 1, and that's going to give us a crest of plus 3. And that concludes our lesson on reflection, interference, and transmission.